Okay, this video is about force and interactions. And before we begin, below is a velocity versus time graph for an object moving in a straight line. Calculate the displacement of the object at 4 seconds. I'd advise you to pause the video and see if you can answer it before I do. Okay, so remember that the area under a velocity time graph is going to give you the displacement. So in the first second here, I have an area of a triangle, which is going to be 1/2 base times height. When I calculate that, I get 1. And from 1 to 2 seconds, I have another triangle. And if I calculate the area of that one, I get 3/2. Adding the 2 to 3 seconds of 3 meters. And then from 3.5, I've got 3/4. Now, because this area of this line here is all above the x-axis for my velocity, that means the velocity of that object is going in the positive direction. At 1 second, the velocity is 0. And at 3.5 seconds, the velocity is also 0. However, something happens from 3.5 to 4, and that is the object is traveling in the negative direction because I have a negative velocity here. So I'm going to subtract the last portion of negative 3/4, ending up with 5.5 meters as my displacement. Today, we're going to resolve vectors into their component parts and calculate the net force. Now, if you've watched the adding vectors mathematically, this is pretty much the same thing, except now you're doing it with forces. So before we get to that, let's talk about forces real quick. Forces are going to be vectors, which simply means they have both magnitude and direction. Here I have a force pulling on this box here. It has a length, a magnitude, and a direction pointing off in that area. Now, because they're forces, each can be resolved into their x and y component parts, as you see here. So we've got a force, we've got an x component of that force, and a y component of that force. So the superposition of forces is just a fancy word for saying that any number of those forces are going to have the same effect as one. For example, I've got this box, mass 1 here, hanging on an incline, and there are 3 forces acting on that mass. First, there's tension going away from the box. That's the first one. The second one is weight pulling the box down. And the third one is this normal force perpendicular to the inclined plane pointing up. And so all 3 of these forces are going to act as one and have the same effect as if they were acting as one force. So the superposition gives us this idea of net force, which means we're going to sum all the forces acting on an object. And just like with the adding vectors mathematically, we've got a resultant vector here, which means I'm going to add up the first force and the second one, and so on and so forth. And a fancy way of saying that is this here, sigma, sum of all forces. So because we have a resultant and it is a vector, we're going to have to resolve that vector into its x and y components. Here I've got the result of the y, which means I'm going to sum up all of the y components. And here I have the resultant of x, meaning I'm going to sum up all of the x components. So let me give you an example here. So we've got 3 professional wrestlers, and they're fighting for the belt. The belt's in the center, and they're all pushing and pulling on it. So the first contestant, we have Big Dog, and he's going to be pulling with 250 newtons at 53 degrees north of west. Coming in the second, we've got Never Lose, pushing to the right, or pulling to the right of that belt. And of course, the third and final contestant, your friend and mine, on steroids. Yes, on steroids. And he's pulling down with 120 newtons downwards. So let's determine the net force acting on this belt. So I strongly encourage you to create a data table just like I have here so we can take an inventory of all of our forces. In the first column, we've got our vectors, F1, F2, and F3, all represented. And then at the bottom, we've got a resultant vector. For the second column, we've got the x components of all of our forces, and then the y component is the third column. So pause the video, see if you can fill in all of these boxes before I start the video back up again. Okay, for the first one, we've got the negative 150.45. I'm going to use my trig ratios for that. And notice that it's pointing in the x direction, in the negative direction, because we define on our x coordinate system, xy coordinate, as anything going to the right is positive, anything to the left is negative. For the y component, it's going up here, so it's 199.66. Now with F2, it's going horizontally, which means I only have an x component, and it's 50 newtons. It's equal to the magnitude of the vector itself, and the y component is 0. And on steroids, same deal, except now it's a different axis. We've got a y component of a negative 120, but our x component is 0. So the next step, I want to add up all of these columns, or these two columns, and I get a new x and y. I get an x component of a negative 100.45 and a y of 79.66. And what I can do with this here is I can create a new vector that's going to go in the negative direction, 100.45, and go up at 79.66. Now I've created a new triangle. From here, it's just the same old routine that we've done with vectors before. We've went ahead and we've wrote our x and y components, and then used the Pythagorean theorem to get us our magnitude of the hypotenuse. And then we're going to use our trig ratios, specifically inverse tangent, to give us the angle of 38.42 degrees north of west. This is, remember, a hard thing for a lot of students, and that is to go west first and go 38.42 degrees north of that, so it's north of west. All right, well, thanks for watching. And remember, if you have questions or you need tutoring in the Phoenix area, go ahead and give me an email at monroe.watson@gmail.com.